Hello and welcome everyone. So today I'm going to discuss two important connection. One is Riemannian connection and second one is Levi-Civita connection. But before I do that, in the last lecture, I actually forgotten one thing. I have explained it to you, but I didn't tell you the definition of the connection coefficient, the so-called Christoffel symbol. So let me just write that down for you. Then we will start with the next topic. Okay. So this is just the formal definition of Christoffel symbols. We have seen where they arrive and they are quite important. So simple definition is that if you have, let M be an m-dimensional manifold with a connection nabla and Ux is your chart, then the Christoffel symbols of connection coefficients so these are your gammas with respect to this chart Ux are basically are MQ functions. So these functions are actually defined in the following manner. So you have nabla del xj del xi, and I have already told you this notation. This del xi is simply del over del xi. Okay, so keep that in mind. Please don't get confused. So these are equals to your gamma ij k del xk, where this I is greater than equals to 1, comma j, and your k is less than equal to n. That's it. They are simple. This is a simple definition of Christoffel symbol. So this was the thing that I left out in the last lecture. I hope you understand all of that. There is nothing quite difficult, and today we will derive an expression for the Christoffel symbol. But before that, let's discuss our new topic. So in this last lecture, when I constructed the definition of covariant derivative of connection, I showed you that on Rn, they satisfy these 6 properties. But when we defined it over a general manifold, we only took these 4 properties, first to fourth. We left out the 5th one and the 6th one. This 5th property is actually known as your, this is related to something called symmetric connection, and this 6th property is actually a condition which is known as metric compatibility. So just like in abstract algebra, you have abelian groups which are completely different. That property is a special one. So in case of connection, you also have these 2 special property which gives you 2 different connections. So let's do that. The first one is actually Riemannian connection. But before that, let's first define the symmetric connection. So what's a symmetric connection? So a connection, let's say nabla, this nabla is said to be symmetric if nabla xy minus nabla yx, this is equals to Lie bracket of x comma y. And this holds for all the vector fields defined over your manifold M. Okay. So this is a simple property, but all the calculation are always being done locally. So let's have a look. What does it locally look like? To see what does it locally look like, let's apply it. Let's consider in particular the basis vector fields, right? X equals to del xi and y equals to del xj. Let's apply that and let's see what happens. So this is quite simple. You have nabla del xi and del xj because this is nabla xy minus nabla del xj del xi, and this is equals to Lie bracket of del xi del xj. And you know it very well that the Lie bracket of basis vector fields is actually 0. So this gives you nabla del xi del xj equals to nabla del xj del xi. Now you can simply say by definition, but as I explained earlier, let me tell you one more time that this nabla del xi del xj, ultimately after operating it, it's going to be a vector field. You have defined the connection from chi-m cross chi-m to chi-n. So ultimately it's going to be a vector field. And if it is a vector field, I can write it as a linear combination of basis vector field. So when we do that, our coefficients are nothing but these connection coefficients. Now pay attention to the indices. Here, this is ij, and on the right hand side, this is ji. So this is a kind of convention. Some people write this upper one, the index that you have in the upper slot, they write it first and then write the lower slot, or some people do the vice versa. Okay. So these are the coefficients and there will be some basis vector and the sum will run over some coefficient, some index, that is k. Okay. Similarly, here also you have this sum. Okay. So this means that simply your Christoffel symbols, these ij and ji, are equal. So whenever you are doing any kind of calculation anywhere, let's say in general theory of relativity, you need to make sure that whatever connection you are using, if it is symmetric, then there is no problem. You can write ij or ji, it doesn't matter. And it turns out that in general relativity, the connection that we are going to use, it is symmetric. But at certain places, it might be possible that the connection is not symmetric. And then writing ji instead of ij is going to be a problematic thing. Okay, so this is a quite simple thing. Globally, the condition looks like this, and locally, the condition simply looks like that. Okay, there is nothing difficult up to here. So from this, we define your Riemannian connection. So the Riemannian connection, a connection nabla on a Riemannian manifold just for the sake of my simplicity, I will write it manifold as MFT. Riemannian manifold M is said to be a Riemannian connection if, so this is your sixth property that we had in our definition of a fine connection. If it satisfies this property, what is this? So this is x, y, z, these angle brackets are nothing but your Riemannian metric. You can also write G of y comma z. Okay. Right now I'm just using the angle bracket notation. This compatibility condition simply says nabla xy comma z plus y comma nabla xz. So you are simply taking the covariant derivative of the first slot, and then in the other case you are taking the covariant derivative of the second slot. So if a connection satisfies this condition, we say that connection is a Riemannian connection. So basically, if a connection satisfies metric compatibility condition, then we say that that connection is a Riemannian connection. Now, later on I will also discuss a separate form, a different form of this metric compatibility condition, which is usually used in general relativity. So it will be useful for those who wish to learn general relativity. So later in the next lecture, I will tell you a different form of this. Okay. So this is your Riemannian connection, which uses the metric compatibility condition. I told you the symmetric condition. Now these two conditions gives you something important, a very important theorem, which is actually the fundamental theorem. What it says is the following, that for our manifold M, there exists a unique connection. The first word is important. This is a unique connection. There exists a unique connection nabla, and it is called Levi-Civita connection. On M, satisfying two properties. The first one is simply your symmetric condition. What was the symmetric condition? Symmetric condition was nabla xy minus nabla yx equals to Lie bracket of xy. And the second condition is your metric compatibility. So the metric compatibility is simply this. So this is the simple theorem, and the proof of it is also quite simple. There is nothing difficult about this proof. And this is the connection that we use in general relativity on space-time. Levi-Civita connection is used on space-time. Well, that's for far future. Right now, let's prove this theorem. So what do we need to prove? We need to prove two things. First is actually the existence. Whenever you have any theorem which says that there exists something, you need to prove the existence. And secondly, it also says that whatever this connection is, it is unique. So let's first prove the uniqueness. Existence is quite simple. Uniqueness is also simple. It's just a long calculation. And there is nothing difficult about this calculation. We also be comfortable with the long calculation in simple cases. Otherwise, how we ever going to do calculation in difficult situation? So let's do this calculation. So first thing that we are going to show is the uniqueness. So how do we show the uniqueness? Well, when we are showing the uniqueness, first we will assume that there exists such a connection. So assume there exists a connection nabla such that it satisfies first and second. So let's call these equation 1 and equation 2. Okay. So we are assuming that it actually satisfies the first and second condition. Okay. So first is the symmetric condition and second one is metric compatibility condition. Now if you look from your second condition, what you have here, so let's do this. Let me write down, let me change one little thing. It doesn't matter much, but let's do that in this manner so that you will have the expression that you have in your books. You can derive in the simple manner also, but let me just write it down so that you get the expressions that you have in your book. There is not a problem if you change the x, y, z. It is still is gonna be same. Okay. So from the second equation, from equation second, see that the value of this on the right hand side, you have this term nabla zx comma y. So this is going to be equal to z x comma y minus x comma nabla zy, right? Now this thing is as it is. Okay. Here x comma nabla zy, you can make use of your symmetric condition. By this symmetric condition, what you will have? This is nabla zy. So the symmetric condition will be something like this. If you rewrite it, nabla zy minus nabla yz equals to leave bracket of z comma y. Okay. So from here, you can get what? This will be nabla yz plus leave bracket of z comma y. Okay. Now Riemannian metric is ultimately your inner product. So it satisfies the properties of the inner product. So you can break this inner product, and after breaking it down, you will get this inner product with nabla yz and one inner product with your leave bracket. Okay. So this is the value that we got for nabla zx comma y, inner product of these two things. So let's call this your equation third. Now in a similar manner, you can actually write two more equations. Don't worry, you don't need to do any calculation. So what are the two more equations? The two more equations are basically this x, y, z and your y, z, x. So you can see it's just simply a cycle. You have three x, y, z. So first you go x, y and z, then you go y, z and x, and then this one z, x, y. Okay. So using the equation third in the similar fashion, you can write it down. You just simply replace x, y, z accordingly. So let me write that down. This is your x, y, z minus y nabla zx. As I told you earlier, it's just a long calculation. There is nothing difficult in this. Y comma leave bracket of x comma z. Okay. And when you do this proof on your own, please do check. There might be some mistake. In case I make some mistake, Please be careful of that. This is y z comma x minus z comma nabla xy minus z comma Lie bracket y comma x. So this is your fourth equation and this one is your fifth equation. Now what you need to do is simply just add this third equation, fourth equation, and then the subtract the fifth equation. Okay, so some terms will cancel out by using certain properties of metric and everything. When you do that, I hope you can do this. So do it on your own. In case anyone has any problem with this, let me know. I will do the entire calculation in the next lecture. Okay, so after doing all the calculation, when you will sum these two equations and subtract the fifth one, you will get a formula, an expression, a long expression, which is quite important. Nabla zx comma y, so this is equals to x yz minus y zx plus z y z xy plus x Lie bracket of y comma z plus y Lie bracket of z comma x and minus z comma Lie bracket of x comma y. You can very well remember this expression. On this side, on the left hand side, if you have zx, you are taking the covariant derivative of x in the direction of z, and then you are taking the inner product with y. Then this expression on the right hand side is quite simple to remember. Just look at the signs of it, plus minus plus, and then here you have plus plus minus, and then you have the cycle xyz yzx zxy. Similarly down here also you can very well remember it. So this expression, this is known as Koszul formula. So what we did up to here, whatever we did up to here is quite simple. We assume that such a connection exists, that it satisfies all the two properties, and then we figure out some expression, did some calculation, and we got this formula. And I say it actually proves, this formula actually proves that our connection is unique. How? The question is, this actually implies that nabla is unique. But how do we know from this formula that the nabla is unique? Well, what we have assumed a connection on our manifold. So manifold is given with a metric. So once we have a manifold, once we have fixed our manifold and fixed our metric, after that, if you look at this formula, the only thing that this formula depends on mainly is your metric. If you have fixed your metric, the connection is going to be a unique connection. The only way this nabla is going to be different one if you change the metric. Otherwise, the metric is fixed, and that's what's happening. Before doing anything, we have fixed our manifold and the metric. And if you are given a manifold and a metric, or you can say you are given a particular Riemannian manifold, and the connection on that Riemannian manifold satisfies this formula, that means it's only depending on the metric. And since the metric is fixed, and that's why this formula proves that our nabla, the connection, is unique. Okay, so let me write down the complete statement so that you can remember. So nabla, this formula gives you that nabla is uniquely determined by the Riemannian metric G on M. Okay, so our uniqueness part is done. I hope there is no problem up to here. Okay, now we need to do is the existence part. How do we do that? So let's do the existence part. So basically what we need to do, that if there is any connection, nabla, first we need to show that it is indeed a connection. So for that we will have to prove those four properties. Secondly, since it is a unique type of connection which satisfies this symmetric condition and metric compatibility condition, so we will also have to show that. Okay, so those things we need to show. But how do we define? To show the existence, first we will have to define some nabla and then check the properties. What we can do? Well, we have the answer in front of us. If such a connection exists, we know from the uniqueness part that that connection will satisfy the Koszul formula. We know that. We want to define a connection first. Only then we are going to check the properties, right? From the uniqueness part, that if such a connection exists, it will satisfy the Koszul formula. So let's define. Why not define the nabla with this formula? So let's define it. So call it equation 6 and let the nabla be defined by equation 6. Okay, so it is defined by equation 6. I hope you understood what I said. We need to show the existence, but first we need to define a connection. Then we will show that it satisfies all the required properties. What definition can we have? Well, if there exists such a connection, we know from the uniqueness part that that connection must satisfy the Koszul formula. And that's why we are defining nabla by our Koszul formula by equation 6. Now let's see if it satisfies all the property. And obviously, since I'm doing a proof of a well-known theorem, you know that it is going to satisfy it. And there are some tedious calculations. So you know all the four properties. Let me do the one. So the first one, if you know, this is nabla z, it is linear in the upper slot. So if you take x1 plus x2 comma y, okay, this one, so it is linear. You can actually break it down. Okay, so how will you do this? So according to the equation 6, what it will be? It will be x1 plus x2, this y comma z minus y z comma x1 plus x2 plus z x1 plus x2 comma y. Similarly, you can write down this also, x1 plus x2 comma leave bracket of y comma z plus you have y comma leave bracket of z comma x1 plus x2 minus z comma leave bracket of x1 plus x2 comma y. Okay, so now you just need to open it up, and when you will open it up, you will find the following thing. You simply get, you should be able to get the following thing: nabla z x1 plus nabla z x2 comma y, and this will give you comma y plus 2 times nabla z x2 comma y. Okay, so please verify it. Okay, in a similar manner, you can also show the second part, that it is also linear with respect to this addition in the lower slot. So you need to check in the similar manner, just open it up by the definition and you can check all the properties. Okay, third and fourth, all those properties. Please do that. In case you have any problem, let me know. I will do it myself. Okay, so up to here, it is quite simple. It was a very simple thing. Proof is a long calculation, but it's not that difficult. Okay, and also keep in mind that you have shown these four properties. Other than that, you also need to show that it is symmetric and it is metric compatible. We are not assuming this anymore. When we were showing the uniqueness, at that time we assumed that it was symmetric and metric compatible. But right now we are not assuming. We need to show that it is indeed symmetric and metric compatible. Okay, so try it. If you have any problem, I will do it on my own. Okay, now let's do one last thing. It is also very simple. So this is an expression. So this is an expression for our Christoffel symbols. And when you do calculations locally, it is quite useful. And this expression is derived from your Koszul formula. So in your Koszul formula, if you see, you have local vector field, simply x, y, z. Now let's ask the question, what would happen if instead of taking general global vector field x, y, z, what if I take these basis vectors, del xi, del xj, and del over del xk. Okay, this should give us some kind of local expression. So let's do that. So let x is equals to del xi, y is equals to del xj, and z is equals to del xk. Okay, let's apply that in the Koszul formula. Your Koszul formula was this: 2 times nabla zx comma y. So this is 2 times nabla zx. Z is del xk, and this is del x I comma y, del x j. Okay, equal to what we had on the right hand side. First we had the x y z. So your x is del xi x and the inner product of yz. So this is del xj del xk. Okay, then we had minus yzx. Your y is del xj, leave bracket of del xk comma del xi, and the third one is your z, del xk and the leave bracket of xy. So this is del xi del xj. And what about the other terms? Well, they will be 0. Why? Because those other terms involve the leave bracket, and the leave bracket of the basis vector field is 0. So the entire inner product is 0. So we don't need to worry about those terms. Okay, we simply have these terms. What else we can do in this? As before, we have done this a lot of time. This is a vector field, so you will have some gammas. This is your ki, let's use L, del XL, comma, del XJ. Okay. Here, what are these? Inner product of del Xi, comma, del Xk. In the first lecture, you have seen that this is nothing but the components of the metric. So del Xi, this is your G, Jk, minus del Xj, similarly, this is your G, Ki, plus del Xk, this is your Gij. Okay. Now these gammas, these are simply coefficients. You can take them out. So this is 2 times gamma L Ki, and then you will have the inner product of del XL, del Xj. What that will be? That will be GLJ. Okay. And this is again on the right hand side, you have same thing, GJK plus, I'm writing this term first, del XK, Gij minus del Xj, GKI. Okay. Now, this is your GLJ. If I write it, this thing, this is nothing but, this is the inverse metric. Okay. So if you apply this on the both side, apply it on both sides, what you will get? This will be 2 times, or let's take our 2 on the right hand side. So here you will have 1 by 2. Now when you will apply this inverse metric GLJ on your metric GLJ, this will be what? This will be simply done. Okay. 1 by 2 GLJ, and you have this entire expression. Xi, so you have this Xi GJK plus del XK Gij minus del Xj GKI. Okay. You can do one more thing. You can just relabel your indices. You can use either this formula, that's not a problem. But let's just simply relabel the indices. These dummy indices, when you relabel them, I with your J and J with your L, then you get this Ij 1 by 2 GLK del Xi GLJ plus del Xj GLI minus del XL Gij. Okay. Please make sure I have not made any mistake while writing down, because it is highly possible when you are dealing with these indices, there might be some mistake. But the proof is quite simple. You just need to take the basis vector and apply them in the Koszul formula. Then do a simple calculation and you will get this expression. If there is any expression which one needs to remember, then this is the expression if you are doing all sorts of different calculation locally. Okay. So that's it for today. I hope you understood all of it. We simply did very simple thing. We defined 2 types of connection, Riemannian connection and Levi-Civita connection. We actually proved that this Levi-Civita connection is actually a unique connection that exists. One more thing that I have not done, even though it is there, in the book, in the first chapter, this is a theorem that I have not done, and it's a very important theorem, that every smooth manifold oh, I should not write this statement like this. For every smooth manifold, a Riemannian metric can be constructed. So if you have your topological manifold and if you can construct the smooth structure, that means you can also construct the Riemannian metric. You always can. I have not done the proof of this because right now I have not explained something called partition of unity. If you are familiar with this topic, you can easily understand the proof of this theorem. It is very simple proof if you understand partition of unity. And don't worry about other things. If you don't know the proof of this theorem, that doesn't mean that you cannot understand the other things. Okay, just keep in mind, I have told you the statement. Just keep in mind that if you have the smooth structure on your topological manifold, you can always have the Riemannian metric. You can always construct a Riemannian metric. Whether at in some question or anywhere you are not given a Riemannian metric on a smooth manifold, that doesn't mean that you cannot construct one. You can always construct one if you have the smooth structure. A smooth structure is enough to be able to construct a Riemannian metric. Okay, we will do the proof of this also someday, but after making some videos on partition of unity. But before that, I will not do that. If you understand partition of unity really well, you can have a look at this proof. It's quite easy. The only difficult thing in that proof is the partition of unity. Okay, so that's it for today. See you in the next lecture. Thank you very much.